Quantum error correction. The breakthrough that makes quantum computers real. For 40 years, quantum computers have been almost impossible to build. Every time scientists added more qubits, errors multiplied faster than computing power. Until November 11th, 2025, when Harvard and MIT prove something remarkable: errors can actually decrease as you scale up. Could this be the moment quantum computing becomes real? Welcome to Sleep Entangled, where quantum breakthroughs and contemplative wonder merge into nocturnal explorations. If you find fascination in these journeys through the frontiers of science, remember to subscribe and let curiosity guide your nights. Now, settle in, breathe slowly, and let's explore the breakthrough that could change computing forever. Chapter 1. The Quantum Computing Dream. Imagine a computer so powerful it could simulate every molecule in a new drug simultaneously. A machine that could factor numbers so large that today's encryption would shatter like glass. A device that could optimize supply chains across entire continents in seconds, model climate change with perfect precision, or discover new materials by exploring millions of atomic configurations at once. This is the promise of quantum computing, and for decades it has remained exactly that, a promise, tantalizingly close yet frustratingly out of reach. The reason is simple yet profound. Quantum systems are extraordinarily fragile. The very properties that make quantum computers powerful, superposition and entanglement, also make them vulnerable to the smallest disturbances: a stray photon, a vibration, a fluctuation in temperature. Even the faint hum of cosmic radiation can destroy the delicate quantum states that computers rely on. For 40 years, physicists and engineers have battled this fragility. They've built quantum computers in refrigerators colder than outer space, shielded them with layers of metal and vacuum, isolated them from every possible source of interference. And still, errors crept in, multiplying faster than the computers could calculate. The fundamental problem was scaling. With classical computers, adding more transistors makes them more powerful. But with quantum computers, adding more qubits, the quantum equivalent of bits, made them more error-prone. It was like trying to build a skyscraper from soap bubbles. The higher you built, the more likely it was to collapse. Until November 11th, 2025. On that day, a team of researchers from Harvard University, MIT, and the quantum computing company QuEra published a paper in the journal Nature that changed everything. They demonstrated a quantum computer with 448 qubits that exhibited fault-tolerant operation, meaning errors decreased rather than increased as the system scaled up. Lead researcher Mikhail Lukin, a professor of physics at Harvard, stated, "This work creates the scientific foundation necessary for the development of practical large-scale quantum computers. For the first time in history, quantum error correction had been fully integrated into a working quantum computer. The dream was becoming reality." To understand why this breakthrough matters, why it represents a turning point in the history of computing, we must first understand what quantum computers are, why they're so powerful, and why they're so impossibly difficult to build. Let's begin with a question. What makes quantum computers different from the device you're listening to this on right now? Classical computers, laptops, smartphones, supercomputers, process information using bits. Each bit is either a 0 or a 1, on or off, true or false. Everything your computer does, from displaying this text to running complex simulations, is built from billions of these binary choices happening billions of times per second. Quantum computers use qubits, and qubits are strange. A qubit can be 0 or 1, or, and here's where quantum mechanics enters, both 0 and 1 simultaneously. This is called superposition, and it's not a metaphor. A qubit in superposition genuinely exists in multiple states at once, collapsing into a definite value only when measured. With 2 classical bits, you can represent 4 possible states: 0, 0, 0, 1, 1, 0, or 1, 1. But you can only hold one of these states at a time. With 2 qubits in superposition, you can represent all 4 states simultaneously. Add a third qubit, and you can represent 8 states at once. A 4th qubit brings it to 16. The growth is exponential. With 300 qubits in perfect superposition, you could represent more states than there are atoms in the observable universe. This is the source of quantum computing's power, where a classical computer must try each possibility one at a time, testing password combinations, simulating molecular interactions, searching through possibilities. A quantum computer can explore vast numbers of possibilities in parallel, collapsing the superposition to reveal the answer. But there's a catch. Actually, there are many catches. First, superposition is fragile. The tiniest interaction with the environment, what physicists call decoherence, causes the qubit to collapse prematurely, destroying the computation. Imagine trying to perform a calculation on a sandcastle while waves crash over it. That's quantum computing. Second, you can't simply read out all the information in a superposition. When you measure a qubit, the superposition collapses to a single outcome. You get one answer, probabilistically chosen from the range of possibilities. Quantum algorithms must be carefully designed to amplify the correct answer and suppress wrong ones through interference effects. Third, and this is the killer, errors accumulate. In a classical computer, you can copy bits, check them, correct errors. But quantum mechanics has a law called the no-cloning theorem. You cannot make a perfect copy of an unknown quantum state. This means the error correction strategies that work for classical computers simply don't work for quantum ones. For decades, this seemed like a fundamental barrier. How can you correct errors if you can't copy the information? How can you build a reliable computer from components that break if you so much as look at them wrong? The answer, it turns out, is clever. Extraordinarily clever. You don't correct errors in individual qubits. You encode information across multiple qubits in such a way that you can detect and fix errors without ever measuring the actual information you're trying to protect. This is quantum error correction, and it was proposed theoretically in the 1990s by physicists like Peter Shor. Yes, the same Shor who invented Shor's algorithm for factoring large numbers. The theory was beautiful, mathematically rigorous, and seemed impossible to implement in practice. Why? Because quantum error correction requires overhead. To protect a single qubit of information, you might need 10, 50, or even 1,000 physical qubits working together, and each of those physical qubits is error-prone, requiring still more qubits to protect them. The overhead compounds and the system grows unwieldy fast. For 30 years, experimental quantum computers remained stuck in what researchers called the Nisky era, noisy intermediate-scale quantum. These devices could perform impressive demonstrations, maintaining quantum states for fractions of a second, running algorithms on dozens of qubits, but they were toys, fundamentally unable to scale to the thousands or millions of qubits needed for practical applications. The November 2025 breakthrough changed that. The Harvard-made QuEra team didn't just demonstrate quantum error correction, they showed it working efficiently, with errors decreasing as qubits were added, and they maintained quantum coherence for more than 2 hours. 2 hours. In a field where maintaining coherence for seconds was considered remarkable, this was a leap of several orders of magnitude, and they did it using a technology that doesn't require the extreme cooling of superconducting qubits or the ultra-high vacuum of trapped ions. They used neutral atoms, individual rubidium atoms held in place by precisely focused laser beams, arranged in programmable patterns like notes on a musical staff. This approach has advantages. Neutral atoms don't interact with each other unless you want them to, which reduces noise. They can be arranged in complex geometries, allowing flexible error correction codes, and crucially, they can operate at much higher temperatures than superconducting qubits, making the systems more practical to build and maintain. So as you rest tonight, imagine atoms suspended in light, each one a qubit, thousands of them arranged in geometric patterns, entangled with their neighbours, performing calculations by dancing through quantum states too complex for any classical computer to simulate. And imagine those calculations running not for milliseconds or seconds, but for hours, protected by layers of quantum error correction that automatically detect and fix mistakes faster than they can accumulate. This is the beginning of practical quantum computing, and it's not a distant dream anymore. It's happening now in laboratories at Harvard, MIT, and around the world. The breakthrough has arrived. In the next chapter, we'll dive deeper into how quantum error correction actually works, exploring the ingenious techniques that allow physicists to protect fragile quantum information without destroying it. Chapter 2 is the fragility problem. Why quantum is so hard. Let us slow down and truly grasp the challenge that quantum error correction solves. Quantum states are, without exaggeration, the most fragile things in the known universe. A single qubit maintaining superposition is like balancing a needle on its point, not on a table, but on the surface of a soap bubble in a hurricane while the ground shakes. To understand this fragility, we need to revisit what superposition actually means at the physical level. When a qubit is in superposition, it exists in a combination of two quantum states. Let's call them 0 angle bracket and 1 angle bracket, using the notation physicists favor. Mathematically, the qubit is in a state like alpha 0 ket plus beta 1 ket, where alpha and beta are complex numbers whose squared magnitudes give the probabilities of measuring 0 or 1. But here's the crucial point. This is not a lack of knowledge. The qubit isn't secretly in state 0 angle bracket or 1 angle bracket and we just don't know which. It is genuinely in both states at once, existing in a quantum superposition that has no classical analogue. This superposition is maintained by quantum coherence, a delicate phase relationship between the two components of the state. Think of it like two synchronized swimmers performing a routine. As long as they maintain perfect timing, the performance is beautiful. But if one swimmer loses the beat, even slightly, the coherence is destroyed. In quantum mechanics, anything that interacts with the qubit can act like an audience member shouting at the swimmers, breaking their concentration. A photon from the environment scattering off the qubit, a magnetic field fluctuation, a thermal vibration. Any of these can entangle the qubit with its surroundings, causing the coherence to leak away into the environment. This process is called decoherence, and it happens fast, frighteningly fast. For superconducting qubits, tiny circuits made from aluminum or niobium, cooled to within 1/100th of a degree above absolute zero, decoherence times are measured in microseconds to milliseconds. That's millionths to thousandths of a second. In that time, the qubit might undergo a few thousand quantum operations before its state decays into noise, For comparison, a classical transistor in your computer can flip billions of times per second for years without error. The gap between classical and quantum reliability is vast, but it gets worse. Not only do individual qubits decohere, but quantum gates, the operations that manipulate qubits, introduce errors. Every time you perform a 2-qubit gate, entangling qubits to perform computation, there's a small probability of error. Maybe the laser pulse is slightly off frequency, or the magnetic field isn't perfectly calibrated, or quantum noise causes an unwanted interaction. In a typical quantum computer, a 2-qubit gate might have an error rate of 0.1% to 1%. That sounds small, but consider, a useful quantum algorithm might require millions or billions of gates. With a 1% error rate, errors accumulate so quickly that the computation becomes meaningless after just a few dozen gates. This is the central problem. Quantum computers need to perform long, complex calculations, but every operation introduces errors and the states themselves decay over time. How can you possibly build a reliable computer from such unreliable components? The classical solution doesn't work. In a classical computer, you use redundancy. Store each bit 3 times. If one bit flips due to cosmic radiation or electrical noise, you can check the majority vote. If 2 bits say 0 and 1 says 1, you assume the correct value is 0 and fix the error, but quantum mechanics forbids this. The no-cloning theorem, proven in 1982 by Wouters, Zurek and Deeks, states that you cannot make an exact copy of an arbitrary quantum state. If you could violate the Heisenberg uncertainty principle, extracting more information from a quantum system than quantum mechanics allows. So you can't just copy a qubit to protect it, and you can't measure it to check if it's correct because measurement collapses the superposition, destroying the information you're trying to protect. It seems impossible, and for many years physicists thought it might be. Then, in 1995, Peter Shor, a mathematician at AT&T Bell Labs, who had just invented a quantum algorithm that could factor large numbers exponentially faster than any known classical algorithm, published a paper titled Scheme for Reducing Decoherence in Quantum Computer Memory. In it, he showed that quantum error correction is possible. The key insight is elegant. You don't protect a qubit by copying it. You protect it by encoding it into an entangled state of multiple qubits in such a way that errors can be detected and corrected without ever learning the actual quantum information. Here's a simplified example called the 3-qubit bit flip code. Suppose you want to protect a single qubit in the state alpha 0 ket plus beta 1 ket from errors that might flip 0 to 1 or vice versa. You start by entangling your one logical qubit with 2 additional physical qubits, creating the entangled state alpha 000 plus beta 111. Notice that if the logical qubit is in state 0, all 3 physical qubits are 0. If it's 1, all 3 are 1. But since the logical qubit is in superposition, the 3-qubit system is in a superposition of both possibilities. Now suppose an error flips one of the 3 qubits. You can detect this by measuring whether the qubits agree with each other, without measuring whether they're 0 or 1. You check, are qubits 1 and 2 the same? Are qubits 2 and 3 the same? If qubit 1 flipped, qubits 1 and 2 will disagree, but 2 and 3 will agree. If qubit 2 flipped, both comparisons will show disagreement. If qubit 3 flipped, qubits 1 and 2 will agree, but 2 and 3 will disagree. By making these parity measurements, checking agreement without measuring the actual values, you can identify which qubit flipped and correct it, all without collapsing the superposition. The logical qubit remains protected. This is the essence of quantum error correction: clever encoding, indirect measurement, and error syndrome detection. Of course, real quantum error correction is far more complex. The 3-qubit code only protects against bit flip errors, but qubits can also suffer phase flip errors, where the relative phase between 0 and 1 gets scrambled. You need codes that protect against both simultaneously. The solution is the surface code, a 2-dimensional lattice of qubits where information is encoded in the correlations between neighboring qubits. Errors are detected by measuring stabilizers, combinations of qubits whose parity should remain constant. When a stabilizer measurement changes, it signals an error, and classical algorithms decode the syndrome to determine which qubits to correct. Surface codes are powerful because they have a threshold property. If the physical error rate is below a certain threshold, about 1% for surface codes, then adding more qubits decreases the overall logical error rate. You achieve fault tolerance. The system becomes more reliable as it scales up. But implementing surface codes in practice is extraordinarily difficult. You need thousands of physical qubits to encode a handful of logical qubits. You need to perform syndrome measurements constantly, faster than errors accumulate, and you need every component, qubits, gates, measurements, to operate below the error threshold. For 2 decades, this seemed out of reach. Experimental quantum computers could demonstrate pieces of error correction, encoding a logical qubit, detecting errors, performing simple operations, but never the full integrated system required for fault tolerance. Until November 2025, when Mikhail Lukin, Dolev Bluvstein, and their colleagues at Harvard and MIT announced they had achieved it. They built a quantum computer using 448 rubidium atoms, trapped and manipulated with laser beams, and demonstrated fault-tolerant operation with logical qubit error rates, suppressed below the physical error rate. They showed that errors decreased as they added more qubits for error correction. They ran quantum circuits for over 2 hours without loss of coherence. They proved that quantum error correction works in practice, not just in theory. As you drift deeper into stillness, picture this: a grid of atoms, each one glowing faintly in the invisible grip of laser light, entangled with its neighbors in intricate patterns. Errors occur, photons scatter, atoms vibrate, quantum states drift. But before those errors can destroy the computation, other atoms measure the syndromes, identify the mistakes, and automatically correct them. The system heals itself continuously, faster than it breaks. This is what the November 2025 breakthrough achieved, and it opens the door to quantum computers that can run for hours, days, perhaps indefinitely, performing calculations that would take classical computers longer than the age of the universe. In the next chapter, we'll explore the technology that made this possible: neutral atom quantum computers, and why atoms trapped in laser beams might be the key to practical quantum computing. Chapter 3: Neutral atoms, computing with trapped light. Picture an atom, not the simplified model you learned in school, electrons orbiting a nucleus like planets around the sun, but the true quantum entity, a cloud of probability, a wave of potential, a shimmer of possibility held together by electromagnetic forces. Now imagine capturing that atom in a beam of light. This is the foundation of neutral atom quantum computing, and it's one of the most elegant approaches to building a quantum computer yet devised. To understand why neutral atoms are so promising, we need to briefly review the other leading technologies. Superconducting qubits, used by Google and IBM, are tiny circuits made from superconducting materials cooled to millikelvin temperatures, colder than interstellar space. They're fast and relatively easy to control, but they require massive refrigeration systems, and they're vulnerable to electromagnetic noise. Coherence times are short, typically tens to hundreds of microseconds. Trapped ions, pioneered by groups at NIST and Oxford, use individual charged atoms held in electromagnetic traps. They have excellent coherence times, seconds to minutes, and very low error rates. But scaling is difficult. Ions repel each other electrically, making it hard to pack many into a small space. And the laser systems required for control are complex and expensive. Neutral atoms offer a compelling middle ground. A neutral atom is just that, neutral. It has no net electric charge, so it doesn't repel other neutral atoms. This means you can pack them closely, creating dense arrays of qubits. The November 2025 breakthrough used 448 atoms, but the technology can scale to thousands or tens of thousands. But how do you trap something with no electric charge? The answer lies in a beautiful trick of light and quantum mechanics called an optical dipole trap. When you shine a laser on an atom, the oscillating electric field of the light induces a tiny electric dipole in the atom. The electron cloud shifts slightly relative to the nucleus. If the laser beam is focused to a narrow spot, the intensity varies across space, and the induced dipole experiences a force pulling the atom toward the region of highest intensity. By focusing many laser beams into a pattern of bright spots, you create a lattice of traps, an optical egg carton, where each dimple holds a single atom. The atoms used in the November 2025 experiment were rubidium-87, a common isotope used in atomic physics. Rubidium is popular because it has convenient energy levels that can be manipulated with readily available lasers, and it's been studied extensively, so its properties are well understood. Each rubidium atom sits in its own trap, held by the gradient of laser intensity, isolated from its neighbours. This isolation is crucial. It means the atoms don't interact unless you want them to, reducing noise and unwanted entanglement. But isolation alone isn't enough for quantum computing. You need to control the atoms, to manipulate their quantum states, and to entangle them with each other. This is where things get intricate. Each rubidium atom has multiple energy levels, different quantum states the electron can occupy. Two of these levels are chosen as the 0 and 1 states of the qubit. By shining laser light at precise frequencies, you can drive transitions between these states, performing single qubit gates, the quantum equivalent of flipping bits. To perform 2 qubit gates, entangling atoms to create the correlations that enable quantum computation, the Harvard-MIT team used a clever technique called the Rydberg blockade. Rydberg atoms are atoms excited to very high energy states, where the outer electron orbits far from the nucleus. In these states, atoms become enormous by atomic standards, hundreds of times larger than in their ground state, and they interact strongly with each other. If you excite a rubidium atom to a Rydberg state, its presence creates an energy shift in nearby atoms, preventing them from also being excited to the same Rydberg state. This is the Rydberg blockade, and it can be used to entangle atoms. Here's how. You apply a laser pulse designed to excite 2 neighbouring atoms to a Rydberg state. If both atoms are in 0, they're not blocked, and you can excite them. If one is in 1, the blockade applies, and only certain combinations of states evolve. By carefully tuning the laser pulses, you can create entangled states between atoms separated by micrometers, a tiny distance in human terms, but vast by atomic standards. This ability to arrange atoms in programmable patterns and entangle them selectively is one of the great strengths of neutral atom systems. Unlike superconducting circuits, where qubits are fixed in a 2-dimensional grid, neutral atoms can be moved and rearranged dynamically, allowing flexible connectivity. In the November 2025 experiment, the team used 448 atoms arranged in a carefully designed pattern, optimized for quantum error correction. They implemented a surface code where logical qubits are encoded in clusters of physical atoms, and stabilizer measurements are performed by entangling neighboring atoms and reading out their parity. Critically, they achieved long coherence times. While individual atoms might decohere on timescales of seconds, the error correction scheme allowed the system to maintain quantum information for over 2 hours, longer than any previous demonstration. Part of this success came from operating at relatively high temperatures. Neutral atom systems don't need the millikelvin temperatures of superconducting qubits. The atoms are laser-cooled to microkelvin temperatures, still cold but warm enough that the refrigeration is much simpler. This makes neutral atom quantum computers more practical and less expensive to build and operate. Another advantage is that neutral atoms are identical. Every rubidium-87 atom is exactly like every other, unlike superconducting qubits, which have slight variations due to fabrication imperfections. This uniformity simplifies calibration and reduces errors. Of course, neutral atom systems have challenges too. Controlling hundreds or thousands of lasers with the precision needed for quantum gates is a formidable engineering problem. Atoms can occasionally be lost from traps due to collisions with background gas molecules or spontaneous emission of photons, and scaling to millions of qubits will require advances in optical systems and control electronics. But the November 2025 results showed that these challenges are surmountable. By integrating all the elements of fault-tolerant quantum computing, qubit encoding, syndrome measurement, error correction, and long-duration operation, the team proved that neutral atoms are a viable path to practical quantum computers. Now, imagine the future. Quantum computers the size of a room filled with laser beams crisscrossing in intricate patterns, trapping thousands of atoms in geometric formations. Classical computers orchestrating the measurements, decoding error syndromes in real time, issuing correction pulses. And at the heart of it all, quantum information flowing through entangled atoms, performing calculations beyond the reach of any classical machine. This future is closer than you might think. Companies like QuEra, Pascal, and Atom Computing are already building commercial neutral atom quantum computers. The November 2025 breakthrough provides the scientific foundation they need to scale up. As you close your eyes tonight, imagine those atoms, tiny motes of quantum possibility, suspended in light, entangled across space, dancing through superposition, each one a qubit, hundreds of them working together, protected by error correction, computing the incomputable. The quantum era is beginning, and it's built from light and atoms, from coherence and entanglement, from the strange and beautiful rules of the quantum world. In the next chapter, we'll explore the critical innovation that made the November 2025 breakthrough possible, how the team achieved fault-tolerant thresholds, and what it means for errors to decrease as you add more qubits. If you're still with me in this late-night journey through quantum breakthroughs, you're part of something rare. A community of curious minds exploring the frontiers of what's possible. A quick subscribe helps others discover this contemplative voyage into quantum computing's deepest challenges. Now let's continue into the heart of the breakthrough, the moment when errors began to decrease instead of multiply. Chapter 4. The Threshold. Crossed. When more qubits mean fewer errors. This chapter marks the turning point, the moment when quantum computing shifted from promise to reality. For decades, adding qubits to a quantum computer made it less reliable. Error rates grew faster than computing power, It was like building a taller tower where each new floor made the entire structure more likely to collapse. But in the November 2025 experiment, something extraordinary happened. Adding qubits for error correction made the system more reliable. Let us unpack why this matters so profoundly. In classical error correction, the logic is straightforward. If your hard drive has a failure rate of 0.1% per year, adding redundancy, storing 3 copies of each file, dramatically increases reliability. The probability that all 3 copies fail is tiny, roughly 0.000001%, 6 orders of magnitude better. But quantum error correction faces a vicious challenge. The very act of detecting errors introduces errors. Every syndrome measurement, every gate operation performed to check for mistakes, has a chance of introducing new mistakes. If the error rate is too high, error correction makes things worse, adding noise faster than it removes it. This is where the threshold theorem comes in. The threshold theorem, proven in the late 1990s by researchers including Dorit Aharonov, Michael Benor and others, states that if the error rate per gate is below a certain threshold, typically around 1% for surface codes, then by using more qubits for error correction, you can suppress logical error rates to arbitrarily low levels. The key word is if. If errors are below the threshold, error correction works. If they're above it, error correction fails, and the system becomes more fragile as it scales. For 25 years, experimental quantum computers operated above the threshold. Physical error rates were too high. Demonstrations could show pieces of error correction working, but never the full fault-tolerant regime where logical qubits outperform physical ones. The November 2025 breakthrough shattered this barrier. The Harvard-MIT QuEra team reported error rates well below the threshold. Their system demonstrated logical qubits with error rates 10 times lower than the underlying physical qubit error rates. This means that by encoding information redundantly across multiple atoms and actively correcting errors, they made the system more reliable than the individual components. Moreover, and this is crucial, they showed that the logical error rate decreased as they added more qubits for error correction. With a small number of qubits per logical qubit, the error rate was modest. With more qubits, forming a larger error-correcting code, the error rate dropped exponentially. This is the signature of fault tolerance. The system doesn't just work, it gets better as it scales. How did they achieve this? The answer involves several innovations working in concert. First, they achieved remarkably low physical error rates. Through careful calibration of laser intensities, frequencies, and pulse sequences, they reduced gate errors to around 0.5%, well below the surface code threshold of roughly 1%. Second, they implemented high-fidelity measurements, measuring whether an atom is in vertical bar 0, vertical bar, or vertical bar 1. Vertical bar is straightforward in principle. You shine a laser that causes atoms in vertical bar 1 vertical bar to fluoresce, emitting photons you can detect while atoms in 0 remain dark. But in practice, measurements can be noisy. Photons can scatter to the wrong detector, or dark atoms can occasionally emit photons due to off-resonant excitation. The team achieved measurement fidelities exceeding 99.5%, meaning that fewer than 1 in 200 measurements gave the wrong result. Third, they used advanced error correction codes optimized for their specific hardware. The surface code is flexible, with many variants. By choosing a code geometry that matched the connectivity of their neutral atom system, they minimized overhead and maximized error suppression. Fourth, and this is where things get sophisticated, they implemented real-time error decoding. In a fault-tolerant quantum computer, syndrome measurements are performed continuously throughout the computation. Each syndrome measurement yields classical data, bits indicating whether errors have occurred. These bits must be processed rapidly to determine which qubits need correction. This decoding problem is computationally hard. The syndromes don't directly tell you which qubits flipped. They provide indirect information that must be interpreted. Classical algorithms, often based on graph theory or machine learning, decode the syndromes and infer the most likely error pattern. The Harvard-MIT team integrated powerful classical processors into their system, performing decoding in real time, fast enough to keep up with the quantum operations. This tight integration of quantum and classical computation is essential for fault tolerance. Finally, they ran the system for over 2 hours. This isn't just impressive, it's transformative. Previous demonstrations of error correction lasted seconds or minutes. Practical quantum algorithms will require hours or days of runtime. The November 2025 result proved that such runtimes are achievable. But here's a subtlety worth understanding. Error correction doesn't eliminate errors, it suppresses them. Even with fault tolerance, logical qubits still have non-zero error rates, just much lower than physical qubits. The game is to make the logical error rate small enough that you can perform the computation you need before errors accumulate to the point of destroying the result. For example, Shor's factoring algorithm, running on a fault-tolerant quantum computer to factor a 2048-bit number, the size used in current encryption, might require billions of gates performed on thousands of logical qubits. Even with logical error rates of 10 to the power of -10, 1 error per 10 billion operations, errors will occur. But as long as they're rare enough, the algorithm will succeed with high probability. This is the promise now within reach. By crossing the fault tolerance threshold, the November 2025 experiment opened the path to quantum computers capable of running arbitrarily long algorithms, protected from errors by layers of redundant encoding. Let's pause and picture what this means concretely. Imagine you're a pharmaceutical researcher trying to design a new drug. Classical computers can simulate small molecules, but proteins, the targets of most drugs, are too large. They contain thousands of atoms, and simulating their quantum behavior is beyond classical reach. A fault-tolerant quantum computer could simulate the protein exactly, exploring how different candidate drugs bind to its active site, predicting effectiveness before you synthesize a single molecule in the lab. Development time could drop from years to months. Or imagine you're optimizing logistics for a global supply chain, routing ships, trucks, planes, balancing costs, delivery times, and carbon emissions. This is a combinatorial optimization problem, exponentially hard for classical computers. A quantum computer using algorithms like QAOA, Quantum Approximate Optimization Algorithm, could find solutions that save billions of dollars and reduce environmental impact. Or consider materials science. Want to design a room temperature superconductor, or a catalyst that efficiently captures carbon dioxide, or a battery with 10 times the energy density of lithium-ion? These problems require understanding quantum interactions in complex systems, exactly what quantum computers excel at. These applications, once theoretical, are now approaching practicality. Because the November 2025 breakthrough proved that fault tolerance works, as you drift towards sleep, imagine the cascading implications, decades of theoretical work distilled into a functioning system. Hundreds of atoms entangled and protected, errors caught and corrected faster than they can spread. Classical and quantum computation merged into a unified whole, each complementing the other. The threshold has been crossed. The era of practical quantum computing is beginning. In the next chapter, we'll explore another critical innovation from the November 2025 work: how the team achieved massive speedups in error correction through a new theoretical framework called Algorithmic Fault Tolerance. Chapter 5: Algorithmic Fault Tolerance, the 100x Speedup. In September 2025, just 2 months before the Harvard-MIT hardware breakthrough, another team published a theoretical advance that complemented it perfectly. Researchers in Germany and the Netherlands introduced a framework called Algorithmic Fault Tolerance, or AFT, published in the journal Nature. This work addressed a bottleneck that had long plagued quantum error correction: the sheer number of operations required to detect and correct errors. Hartmut Neven, lead of Google Quantum AI, called it a very significant advance. To understand AFT, we need to grasp the overhead problem in quantum error correction. Recall that protecting a single logical qubit requires many physical qubits, often dozens or hundreds depending on the error rate and the code. But it's not just the qubits that scale up. The number of operations, gates and measurements required to run error correction grows rapidly too. In a standard surface code implementation, you must perform syndrome measurements every cycle. For a medium-sized code with 100 physical qubits, this might involve hundreds of 2-qubit gates per cycle. If you're running the computer for millions of cycles, that's billions of gates. Each gate takes time, each measurement takes time, and even with parallelization, the time required for error correction can dominate the computation, making the quantum computer slower than expected. AFT changes this by reorganizing how error correction is performed. The key insight is that not all errors are equally urgent. Some errors, if left uncorrected for a few cycles, won't immediately destroy the computation. Others need to be fixed right away. By analyzing the structure of the quantum algorithm being run, AFT identifies which errors to prioritize and which can wait. This is similar to how a skilled editor proofreads a document. Instead of checking every letter sequentially, they scan for glaring mistakes first, misspelled words, grammatical errors, and leave minor issues for later passes. The document is still correct, but the proofreading is faster. In quantum error correction, AFT uses classical algorithms to predict which syndromes are likely to indicate serious errors based on the current state of the computation. Syndrome measurements are scheduled accordingly, focusing computational resources where they're most needed. The result? A 10 to 100-fold reduction in the time required for error correction, depending on the algorithm and code. For the November 2025 experiment, this was crucial. Running error correction for over 2 hours requires billions of operations. Without AFT-inspired optimizations, the system would have been overwhelmed. The Harvard-MIT team integrated ideas from AFT into their control software, dynamically adjusting syndrome measurement schedules to minimize overhead while maintaining fault tolerance. This synergy between hardware improvements, low error rates, long coherence times, and software innovations, efficient error correction, is what made the breakthrough possible. But AFT represents more than just a speedup. It's a philosophical shift in how we think about error correction. Traditionally, error correction is passive and uniform. You measure all syndromes all the time, treating every qubit equally. AFT makes error correction active and adaptive. The system learns, in real time, where errors are likely and adjusts its strategy. This adaptability hints at a future where quantum computers are self-optimizing, using machine learning to tune their error correction based on the specific algorithms they're running and the specific noise patterns they encounter. Imagine a quantum computer that learns from experience. Over days of operation, it observes which qubits are more error-prone, which gates introduce the most noise, which measurement patterns are most effective. It adjusts its error correction strategy, becoming more reliable over time. We're not there yet, but AFT is a step in that direction. Let's ground this in a concrete example. Suppose you're running Shor's algorithm to factor a large number. Shor's algorithm has several stages: initialization, quantum Fourier transforms, modular exponentiation, and readout. Some stages are more error-sensitive than others. During initialization, the qubits are being prepared, and small errors have minimal impact. They'll be corrected as the algorithm progresses. During modular exponentiation, errors are more dangerous as they can propagate through entangled qubits, corrupting the result. AFT would allocate more error correction resources to the exponentiation stage, performing frequent syndrome measurements and corrections while relaxing the correction frequency during initialization. The total number of operations decreases, and the algorithm runs faster without sacrificing reliability. For researchers at Google, IBM, and other companies working on quantum algorithms, AFT is a game changer. It means that algorithms previously thought to require prohibitively large quantum computers might be runnable on smaller systems with clever error management. It also raises intriguing theoretical questions. If error correction can be optimized based on the algorithm, what's the ultimate limit? How much can overhead be reduced? Can we develop error correction codes specifically tailored to particular algorithms, trading generality for efficiency? These questions are at the frontier of quantum information theory, and the November 2025 breakthroughs, both in hardware and software, provide the experimental platform to explore them. As you rest, consider this. Computation isn't just about raw power, it's about efficiency, cleverness, and optimization. The quantum computers of the future won't just be bigger, they'll be smarter, adapting in real time to the tasks they're performing and the errors they encounter. Algorithmic fault tolerance is one piece of this puzzle, a glimpse of how quantum and classical computation will blend, each enhancing the other in ways we're only beginning to understand. In the next chapter, we'll explore the applications that are now coming within reach and what the November 2025 breakthrough means for industries ranging from pharmaceuticals to finance to climate modeling. Chapter 6: Applications on the Horizon. What fault-tolerant quantum computers will do. The November 2025 breakthrough was not an end but a beginning. It proved that fault-tolerant quantum computers are possible. The next question is, what will we use them for? This question has driven quantum computing research for decades. The promise has always been clear. Quantum computers will solve problems beyond the reach of classical machines. But which problems exactly? And how soon? Let's explore several domains where fault-tolerant quantum computers will have transformative impact. Drug discovery and molecular simulation. Simulating molecules is one of the most natural applications for quantum computers. Molecules are quantum systems, governed by the Schrödinger equation. To understand how a drug binds to a protein, you need to calculate quantum interactions, electron distributions, bond energies, reaction pathways. Classical computers struggle with this. For small molecules, quantum chemistry software can provide approximate solutions. But for large molecules like proteins, the problem becomes intractable. The number of quantum states grows exponentially with the number of electrons, overwhelming even supercomputers. A fault-tolerant quantum computer could simulate large molecules exactly, predicting properties like binding affinity, stability, and reaction rates. This would revolutionize drug development. Current drug discovery is slow and expensive, often taking over a decade and billions of dollars to bring a new drug to market. Much of this time is spent on trial and error, synthesizing candidate molecules, testing them in the lab, and discarding those that don't work. With quantum simulation, researchers could screen millions of candidates computationally, identifying the most promising ones before synthesizing anything. This would accelerate development, reduce costs, and enable personalized medicine, drugs tailored to individual patients' genetic profiles. The November 2025 breakthrough brings this closer. With fault-tolerant quantum computers, we can run algorithms like the variational quantum eigensolver, VQE, or quantum phase, estimation for molecules with hundreds of atoms, a regime inaccessible to classical methods. Materials, science, and chemistry. Beyond drugs, quantum computers will enable the design of new materials, room-temperature superconductors, ultra-efficient solar cells, batteries with 10 times today's energy density, catalysts for carbon capture. Consider nitrogen fixation, the process of converting atmospheric nitrogen into ammonia for fertilizers. Currently, this is done using the Haber-Bosch process, which requires high temperatures and pressures and consumes about 2% of global energy. Nature accomplishes the same task at room temperature using nitrogenase enzymes, but we don't fully understand how. Quantum simulation could reveal the mechanism, enabling the design of synthetic catalysts that mimic nature's efficiency. The impact on agriculture and energy use would be enormous. Or consider superconductors. Materials that conduct electricity with zero resistance could transform energy grids, eliminating transmission losses. But current superconductors require extremely low temperatures. Discovering a room temperature superconductor would be revolutionary, and quantum computers could search the vast space of possible materials far faster than classical trial and error. Optimization and machine learning. Many problems in logistics, finance, and AI involve optimization, finding the best solution from an enormous number of possibilities. For example, optimizing global shipping routes to minimize cost and carbon emissions involves considering thousands of variables: ship speeds, fuel prices, port schedules, weather patterns. The number of possible routes grows combinatorially, and finding the optimal one is NP hard. Quantum algorithms like QAOA, Quantum Approximate Optimization Algorithm, can explore these possibilities more efficiently than classical algorithms. While they may not always find the absolute optimum, they can find very good solutions quickly. In machine learning, quantum computers could accelerate training of neural networks, optimize hyperparameters, or enable entirely new architectures. Quantum machine learning is still a young field, but fault tolerance will allow researchers to explore it deeply. Cryptography and security. This is the application that brought quantum computing to public attention. Shor's algorithm, running on a fault-tolerant quantum computer, can factor large numbers exponentially faster than the best-known classical algorithms. Current encryption, RSEA, used to secure online transactions and communications, relies on the difficulty of factoring. If a sufficiently large quantum computer were built, RSA would be broken, with profound implications for cybersecurity. The November 2025 breakthrough doesn't immediately threaten encryption. The system demonstrated had 448 qubits, and factoring a 2048-bit RSA key would require millions of qubits. But it's a step on that path. Governments and companies are already preparing by developing post-quantum cryptography, encryption algorithms resistant to quantum attacks. The transition will take years, but it's urgent. Data encrypted today could be stored and decrypted later when quantum computers are powerful enough, a threat known as harvest now, decrypt later. Climate modeling and scientific simulation. Understanding climate change requires simulating complex systems, atmospheric chemistry, ocean currents, ice sheet dynamics. These simulations involve quantum processes, molecular interactions, radiative transfer that classical computers approximate crudely. Quantum computers could model these processes more accurately, improving climate predictions and helping us design better interventions. Similarly, in fundamental science, simulating the behavior of matter in extreme conditions, modeling nuclear reactions for fusion energy, understanding quantum chromodynamics, the theory of quarks and gluons, quantum computers offer tools unavailable classically. Financial modeling. In finance, quantum computers could optimize portfolios, price complex derivatives, model risk. Monte Carlo simulations, widely used in finance, involve exploring random scenarios to estimate probabilities. Quantum algorithms can achieve quadratic speedups for such problems, drastically reducing computation time. High-frequency trading firms and banks are investing in quantum research, anticipating that fault-tolerant systems will provide competitive advantages. The timeline. When will this happen? The November 2025 breakthrough answered the if question. Yes, fault-tolerant quantum computers are possible. The when question remains. Most experts estimate that practical, large-scale, fault-tolerant quantum computers capable of running algorithms like Shor's or simulating complex molecules are still 10 to 20 years away. Building systems with millions of qubits integrated with sophisticated error correction is an engineering challenge of immense scale. But progress is accelerating. Companies like QuEra, IonQ, PsiQuantum, and Atom Computing are building commercial quantum computers. Governments are investing billions, and the November 2025 results provide a clear roadmap. Within a decade, we may see quantum computers tackling specific high-value problems in drug discovery or materials science. Within 2 decades, quantum computers could be routine tools in research and industry, as ubiquitous as supercomputers are today. The transformation will be gradual but profound. Not a sudden revolution, but a steady expansion of what's computable, what's designable, what's knowable. As you close your eyes and settle into stillness, imagine this future. Molecules designed atom by atom, optimized in silico before synthesis. Materials with properties never seen in nature, discovered through quantum exploration. Algorithms running on machines that harness the full strangeness of quantum mechanics, exploring possibility spaces vast beyond imagining. The November 2025 breakthrough opened the door. The journey through that door will define the coming century. In the next chapter, we'll explore the theoretical foundations that made this possible, diving into the mathematics of quantum error correction and the codes that protect fragile quantum information. Chapter 7. The Mathematics of Protection, Surface Codes and Stabilizers. For those willing to venture deeper, this chapter explores the elegant mathematics underlying quantum error correction. Don't worry if the details blur. There is beauty in the structure itself, in the cleverness of the solution. Quantum error correction is built on a foundation of group theory, linear algebra, and graph theory. But at its heart is a simple idea. Encode information redundantly in a subspace of a larger Hilbert space, and use symmetries to detect when errors push you out of that subspace. Let's start with the concept of a stabilizer. In quantum mechanics, observables are represented by operators, mathematical objects that act on quantum states. Some operators leave certain states unchanged, returning the same state, perhaps with a phase factor. Such states are called eigenstates of the operator, and the operator is said to stabilize them. For example, consider the Pauli operators, which act on a single qubit. X flips, großroot equal 1, and vice versa, bit flip. Z flips the phase of Doshka1 relative to Dusturstro, phase flip. Y is a combination of X and Z. The state plus is equals Sterron plus Brastner, divided by the square root of 2 is an eigenstate of X with eigenvalue plus 1, meaning X plus greater than equals greater than. We say X stabilizes greater than. Now consider multiple qubits. You can construct operators that act on several qubits simultaneously, products of Pauli operators. For example, Z1, Z2 measures where the qubits 1 and 2 have the same phase. A stabilizer code defines a subspace of quantum states that are simultaneously Ian states of a set of stabilizer operators. This subspace is the code space, and states within it represent error-free logical qubits. If an error occurs, say an X flip on qubit 1, the state is pushed out of the code space. It's no longer stabilized by all the stabilizers. By measuring the stabilizers without measuring the qubits themselves, you detect which stabilizers failed, revealing the error syndrome. This is the magic. You measure operators, not qubits. The measurement tells you whether an error occurred and where, without collapsing the superposition of the logical qubit. The surface code is a specific stabilizer code defined on a two-dimensional lattice of qubits. Picture a checkerboard with qubits on the vertices. Each square on the board corresponds to a stabilizer, either an X-type stabilizer, product of X operators on the 4 qubits around the square, or a Z-type stabilizer. Logical qubits are encoded in the topology of the lattice. A logical X operation corresponds to a string of X flips stretching across the lattice from one edge to the opposite edge. Similarly, a logical Z operation is a string of Z flips running perpendicular. When an error occurs, it creates defects, pairs of syndrome violations. These defects are endpoints of error chains. By measuring all stabilizers, you detect the locations of defects. Classical decoding algorithms then infer the most likely error and apply corrections. The surface code is powerful because 1. It requires only nearest neighbor interactions, making it easier to implement in hardware. 2. It has a high threshold, around 1% error rate. 3. It can be implemented on a two-dimensional lattice, compatible with many physical platforms. But it has a drawback: high overhead. To encode a single logical qubit with reasonable error suppression, you might need 100 or more physical qubits. Achieving very low logical error rates requires thousands of physical qubits per logical qubit. This is where the November 2025 breakthrough is so significant. The Harvard-MIT team demonstrated that even with this overhead, fault tolerance works. The trade-off is acceptable because the logical qubits are so much more reliable. There are other codes, color codes, LDPC, low-density parity check codes, topological codes with different geometries, each with trade-offs between overhead, threshold, and implementation complexity. Research continues to find codes better suited to specific hardware. Here's a playful way to think about it. Imagine you're transmitting a message across a noisy channel, a room full of people whispering the message from one to another. Errors creep in. People mishear words, add syllables, swap letters. Classical error correction would have multiple people repeat each word, and you'd take a majority vote. But you can't do that in quantum mechanics because you can't copy states. Quantum error correction is like encoding the message into a song where the melody and rhythm carry redundancy. If someone sings a wrong note, you can hear it because it breaks the harmony, and you correct it without needing to know the entire song. The code space is the set of harmonious melodies, and errors are dissonant notes that syndrome measurements detect. For those fascinated by mathematics, I encourage you to explore the literature. The foundational papers by Shor, Steen, Kitaev, and others are works of profound creativity. The surface code was introduced by Kitaev in 1997, building on earlier ideas from topological quantum field theory. But even if the mathematics feels distant, the essence is clear. Quantum error correction transforms an impossible problem into a solvable one through layers of clever encoding, indirect measurement, and symmetry. As you drift into rest, let the abstractions settle softly. Mathematics as a language for describing nature, equations as maps of possibility, quantum states protected by symmetries, information encoded in topology, errors detected without destruction. This is the foundation upon which the November 2025 breakthrough was built, and it opens pathways to technologies we're only beginning to imagine. In the next chapter, we'll explore the competitors and alternatives, other approaches to quantum computing, and why neutral atoms with error correction represent one promising route among several. Chapter 8: The Quantum Race, Competing Technologies and Approaches. Quantum computing is not a single technology but a diverse ecosystem of approaches, each with strengths and challenges. The November 2025 neutral atom breakthrough is one milestone in a broader race involving multiple platforms. Let's survey the landscape. Superconducting qubits. This is the approach taken by Google, IBM, and Rigetti. Superconducting qubits are tiny circuits made from materials like aluminum or niobium, cooled to millikelvin temperatures. Advantages: fast gates, nanoseconds, well-developed fabrication techniques, borrowed from semiconductor industry, good connectivity, qubits can be wired flexibly. Challenges: short coherence times, microseconds to milliseconds, requires extreme cooling, dilution refrigerators, sensitivity to electromagnetic noise. Google's 2019 quantum supremacy demonstration used 53 superconducting qubits. IBM recently announced a 1,000 qubit superconducting processor. These systems are impressive but still operate in the NISQ regime, not yet fault-tolerant. Trapped ions. Companies like IonQ, Honeywell, now Quantinuum, and Alpine Quantum Technologies use individual ions trapped by electromagnetic fields. Advantages: long coherence times, seconds to minutes, high-fidelity gates, 99.9% plus. All ions are identical, no calibration variability. Challenges: slow gates, microseconds to milliseconds, difficult to scale, ions repel each other, limiting density. Complex laser systems. Trapped ion systems have achieved some of the highest gate fidelities, making them strong candidates for fault tolerance. But scaling to thousands of qubits is a major engineering challenge. Photonic qubits. Photons, particles of light, can encode quantum information in properties like polarization or path. Companies like Xanadu and PsiQuantum are developing photonic quantum computers. Advantages: operate at room temperature. Photons don't decohere easily, they don't interact much with their environment. Can use existing telecommunications infrastructure. Challenges: generating single photons reliably is hard. Photon-photon interactions needed for gates are weak. Measurements are destructive. Photons are absorbed when detected. Photonic quantum computing is promising for specific applications like quantum communication and certain sampling problems, but general-purpose photonic quantum computers face significant hurdles. Topological qubits. Microsoft is pursuing a radically different approach. Topological qubits based on exotic particles called Majorana fermions, or Majorana zero modes. The idea is that quantum information is encoded in global topological properties of a system, making it inherently robust to local errors. If realized, topological qubits would need far less error correction, but there's a catch. Majorana fermions are hypothetical. As of 2025, their existence in the solid state remains unconfirmed. Microsoft has invested heavily, but the technology is speculative. Neutral atoms, QuEra, Pascal, atom computing. The November 2025 breakthrough demonstrated the potential of neutral atoms. Advantages, as discussed: identical qubits, scalable to large arrays, long coherence times, operates at higher temperatures than superconducting qubits. Challenges: laser control complexity, occasional atom loss. Rydberg blockade gates are slower than superconducting gates. QuEra, the company collaborating with Harvard and MIT, is commercializing neutral atom systems. Pascal in France and atom computing in the US are also advancing the technology. Silicon spin qubits. Intel and others are exploring qubits based on electron spins in silicon, leveraging decades of semiconductor manufacturing expertise. Advantages: compatibility with existing chip fabrication, small size, potentially very high density, long coherence times similar to trapped ions. Challenges: precise control at the nanoscale is difficult, still early stage, few qubits demonstrated. If silicon spin qubits can be scaled, they could benefit from the massive infrastructure of the semiconductor industry. The verdict: no single winner yet. Each approach has passionate advocates, and it's possible that different technologies will excel at different tasks. Superconducting qubits might dominate optimization problems, where speed is critical. Trapped ions might be best for high-precision simulations. Photonic systems might form the backbone of quantum networks. The November 2025 neutral atom result doesn't declare neutral atoms the winner. It proves that one path to fault tolerance is viable. Other platforms will likely cross similar thresholds in the coming years. What's striking is the convergence. Regardless of platform, the roadmap is clear. Achieve low enough error rates, implement error correction, scale up. The November 2025 breakthrough shows this roadmap works. Competition is healthy. It drives innovation, accelerates progress, and ensures redundancy. If one approach stalls, others continue. And researchers learn from each other, borrowing ideas across platforms. Here's a lighter thought. The quantum computing field resembles the early days of aviation. In the 1900s, dozens of designs competed: biplanes, monoplanes, different engine types, control surfaces. Some ideas flourished, others faded. But the diversity was essential. Experimentation revealed what worked. Today's quantum computers are the Wright Flyer and the Spirit of St. Louis, pioneering machines proving that flight is possible. Tomorrow's quantum computers will be the 747s and F-22s, powerful, reliable, specialized. And as you settle into the night, imagine this diversity of technologies, each one a different attempt to harness the quantum realm. Atoms in light, ions in traps, circuits in cold, photons in waveguides. Each a bet on a different vision of the future, each contributing to the collective understanding. The quantum era won't belong to a single technology. It will be a mosaic, with different tools for different problems, all built on the same fundamental principles of superposition, entanglement, and correction. In the next chapter, we'll confront the challenges ahead, what obstacles remain, and what must happen for quantum computers to transition from laboratory curiosities to everyday tools. Chapter 9. The challenges ahead, what's still missing. The November 2025 breakthrough is monumental, but it's not the finish line. Significant challenges remain between today's 448 qubit demonstration and tomorrow's million-qubit machines solving real-world problems. Let's soberly assess what must still be achieved. Scaling to millions of qubits. The Harvard-MIT system demonstrated fault tolerance with 448 qubits. Practical applications, factoring large numbers, simulating complex molecules, optimizing large systems, will require millions of qubits. Scaling by 3 orders of magnitude is not trivial. It requires laser systems capable of controlling millions of atoms with individual precision, classical processors powerful enough to decode error syndromes from millions of measurements per second, refrigeration and environmental control to maintain stability across the entire system, error rates that remain low as the system grows. Neutral atom platforms have inherent advantages for scaling. Atoms can be arranged in dense 2D or 3D arrays, but engineering challenges abound. Reducing overhead. Current error correction codes require 100 to 1000 physical qubits per logical qubit to achieve low error rates. This overhead is acceptable for demonstrations but costly for large systems. Better codes, lower overhead, higher thresholds would accelerate progress. Research into LDPC codes, which have favorable scaling properties, is promising, but implementing them in hardware is complex. Improving gate speeds. Neutral atom gates are slower than superconducting or photonic gates. A Rydberg blockade gate might take microseconds, compared to nanoseconds for a superconducting gate. For algorithms requiring billions of gates, speed matters. Researchers are exploring faster gate mechanisms, optimized pulse sequences, and parallelization strategies. Maintaining stability. Running a quantum computer continuously for hours or days requires unprecedented stability. Temperature fluctuations, vibrations, magnetic field drift, any of these can degrade performance. The November 2025 experiment maintained coherence for over 2 hours, impressive but still short of the days or weeks needed for some applications. Achieving this will require advances in environmental control and monitoring. Integrating classical and quantum systems. Fault-tolerant quantum computers are hybrid systems. Quantum hardware performs the computation, classical hardware decodes errors and issues corrections. The classical side is often underestimated. Real-time decoding of error syndromes from millions of qubits is a formidable computational task. As quantum systems scale, classical coprocessors must scale too, creating a tight feedback loop. Machine learning might help here, training neural networks to decode syndromes faster than traditional algorithms. Developing practical algorithms. Even with fault-tolerant hardware, we need algorithms that leverage it. Shor's factoring algorithm is famous, but it has limited applications. QAOA for optimization is promising but not yet proven to outperform classical methods on practical problems. Quantum algorithm development is an active field. Researchers are discovering new algorithms, refining existing ones, and identifying problems where quantum computers have genuine advantages. Economic viability. Building and operating quantum computers is expensive. Dilution refrigerators, high-power lasers, specialized electronics, and expert personnel all cost money. For quantum computers to transition from research tools to commercial products, they must provide value exceeding their cost. This might happen first in high-value niches, pharmaceuticals, finance, defense, where even modest speedups justify expense. Over time, as technology matures and costs fall, quantum computing could become accessible to a broader range of industries. Workforce and expertise. Quantum computing is a multidisciplinary field requiring expertise in physics, engineering, computer science, and mathematics. There aren't enough trained quantum engineers to meet future demand. Universities and companies are investing in education, but training a quantum workforce takes time. This human challenge is as significant as the technical ones. Public understanding and policy. Quantum computing has implications for security, privacy, and geopolitics. Governments are investing in quantum research, aware of its strategic importance. But public understanding lags. Misconceptions abound. Quantum computing is not magic. It won't solve every problem, and it's not just faster classical computing. Clear communication, responsible policy, and international cooperation will be essential as the technology matures. Despite these challenges, progress is accelerating. Here's a plausible timeline: 2025 to 2027. Multiple platforms cross the fault tolerance threshold. Systems with 1,000 to 10,000 qubits are demonstrated. 2028 to 2030. First practical applications emerge in materials science and drug discovery. Quantum computers tackle problems beyond classical reach, though still in specialized domains. 2031 to 2035. Scaling continues. Systems with 100,000 plus qubits become operational. Quantum algorithms mature, and commercial quantum computing services expand. 2036 to 2040. Quantum computers become standard tools in research and industry. The first cryptographically relevant quantum computers appear, prompting full transition to post-quantum encryption. This timeline is speculative, but it reflects the current trajectory. The November 2025 breakthrough suggests that optimism is warranted. As you drift towards sleep, reflect on this. Every transformative technology, electricity, flight, computing, faced skeptics and obstacles. Progress was uneven, setbacks occurred. But persistence, ingenuity, and collaboration prevailed. Quantum computing stands at a similar threshold. The November 2025 result proves that the dream is achievable. The challenges ahead are real, but so is the determination of thousands of researchers worldwide. The quantum future is not guaranteed, but it's within reach, and reaching it will reshape science, industry, and society in ways we're only beginning to imagine. In the final chapter, we'll reflect on what this all means for science, for humanity, and for our understanding of reality itself. Chapter 10. The meaning of the breakthrough, science, humanity, and the quantum future. We've journeyed through technical details, qubits, error codes, thresholds, atoms in light. But let's step back now and ask, what does this really mean? The November 2025 breakthrough is more than an engineering achievement. It's a statement about human capability, about our ability to manipulate nature at its most fundamental level, about the power of theoretical insight to guide practical invention. For 40 years, quantum error correction was a beautiful idea that seemed impossible to realize. Physicists proved theorems, designed codes, wrote papers. but experiments lagged far behind. The gap between theory and practice yawned wide. Then, on November 11, 2025, that gap closed. The experiment matched the theory. Fault tolerance works. The impossible became possible. This is the pattern of science at its best. Theory predicts, experiment confirms, technology follows. Einstein predicted gravitational waves in 1916. LIGO detected them in 2015. Higgs postulated a field giving mass to particles in 1964. The LHC found the Higgs boson in 2012. Now, quantum error correction joins this lineage. From Shor's 1995 paper to the 2025 demonstration, 3 decades of effort, culminating in validation. But this is also different. Gravitational waves and the Higgs boson are discoveries about the universe. Quantum error correction is an invention, a way of bending nature to our purposes, using its rules to overcome its limitations. This speaks to something profound about human creativity. We don't merely accept the world as given. We engineer it, redesign it, build tools that transcend natural constraints. Fire extended our metabolism. Writing extended our memory. Computers extended our cognition. Quantum computers extend our reach into possibility space itself, allowing us to explore configurations of reality inaccessible to classical thought. There's a philosophical dimension too. Quantum mechanics is strange. Superposition, entanglement, uncertainty. For over a century, physicists have debated what it means. Does observation create reality? Do parallel worlds exist? Is there hidden structure beneath the quantum surface? Quantum computing doesn't answer these questions, but it engages them practically. When you encode information in superposition and manipulate it with gates, you're not just calculating, you're interacting with quantum ontology, using its strangeness as a resource. In a sense, quantum computers are experiments in the nature of reality, probing the boundaries of what exists and what can be known. Here's a gentle thought. The universe is quantum, matter, energy, light, all governed by quantum rules. Classical physics is an approximation, a limit valid when systems are large and interactions average out. We live in a quantum universe, but for most of history we've understood it only approximately through classical intuitions. Quantum mechanics reveal the deeper truth, but applying it was difficult. Calculations were hard, experiments delicate, applications limited. Quantum computers change this. They let us work directly in the quantum substrate, solving problems formulated in nature's native language. It's like learning to think in quantum rather than translating everything into classical terms. This shift might be as significant as the shift from geocentrism to heliocentrism, or from Newtonian to relativistic physics. Not just new tools, but a new relationship with reality. And yet, for all its strangeness, quantum computing is also practical. It will design drugs, optimize logistics, model climate. The ethereal and the concrete merge. This duality captures something essential about science. It seeks truth and utility, understanding and application. The same equations that describe abstract superpositions also guide the laser pulses controlling atoms. Theory and practice are inseparable. As we look ahead, the quantum era presents challenges and opportunities. Challenges. Encryption will need rethinking. The workforce must be trained. Ethical questions about access and equity will arise. Who benefits from quantum technologies and who might be left behind? Opportunities. Diseases cured, materials discovered, energy systems optimized, scientific mysteries unraveled. The potential is vast, but perhaps the deepest impact will be cognitive. As quantum computers become tools we use regularly, they'll shape how we think. Future engineers will grow up with quantum intuition, understanding superposition and entanglement as naturally as today's engineers understand circuits and code. This could lead to conceptual breakthroughs we can't yet imagine. New physics, new mathematics, new philosophies built on quantum foundations. The November 2025 breakthrough is a milestone on this journey. It proves that we can build quantum computers that work, that error correction is practical, that the quantum era is beginning, but it's just one step. The road ahead is long, filled with challenges and surprises, and that's as it should be. Science doesn't offer quick resolutions. It's a journey of discovery, driven by curiosity and perseverance. As you rest tonight, imagine the atoms in your body, the photons striking your retina, the electrons flowing through your neurons, all quantum, all governed by the same rules that Harvard and MIT harnessed to build a fault-tolerant computer. You are a quantum system, observing a quantum universe, thinking quantum thoughts, whether you realize it or not. The quantum computers being built are not alien machines but extensions of what you already are. Matter and energy exploring its own nature. Perhaps this is the ultimate meaning of quantum computing. It's not just technology but self-discovery, humanity learning to speak the language of the universe and using it to create, to explore, to understand. The November 2025 breakthrough is a word in that language, a sentence in the story we're writing. The chapters ahead will be written by researchers, engineers, dreamers, perhaps by some of you listening now. The quantum future is not inevitable, but it's within reach. And reaching it will require not just technical brilliance but vision, collaboration, and the courage to pursue ideas that seem, at first, impossible. Thank you for joining this exploration. May your dreams be filled with possibilities collapsing into realities one quantum moment at a time. And as we reach the end of this journey through quantum error correction, take a moment to let the magnitude settle. From fragile qubits that collapsed at a whisper, to fault-tolerant systems running for hours, this is the breakthrough that transforms quantum computing from dream to reality. If this exploration has stirred wonder within you, I invite you to subscribe to Sleep Entangled for more deep dives into the frontiers of science. Like this video to help others discover how Harvard and MIT made the impossible possible. And share your thoughts. What excites you most about quantum computing's future? This is Sleep Entangled, where quantum breakthroughs and contemplative understanding merge into meaning. Until we meet again in the quantum realm, rest easy, knowing that impossibilities are merely problems awaiting clever solutions. The quantum era has begun.